Okay, so we will talk about Bellman Ford algorithm. So, this is this can handle the negative edges. So, here we are allowing the negative cycle. So, like in dextrose we restrict ourselves from the negative cycle. So, for that we took our this weights are all positive. So, that there should not be any negative cycle, but here this can handle that Bellman Ford. So, here our input is, so this is also a single source shortest path problem. So, we have a graph G comma E, and here our edge is, we are allowing negative edge also, and we have a source vertex, and either it should give us delta of S comma E V from all other vertex V, or it should report that there is a negative cycle in the graph. Okay. So, let us write the code for Bellman Ford algorithm. So, this is G W from E to R, and we have a source vertex. Okay. So, initialization step is same as the dextrose. So, we will just assign the degree of S is 0 and the degree of any other vertices as infinity, V minus S. That means, these are not yet explored. So, this is the initialization step, which is same as the initialization, which is same as which is same as the Bellman Ford dextrose algorithm. Now, what we do? We do the branch of relaxation. We check each edge and we will see whether we can relax that corresponding vertex. So, that is the idea. So, and how many times we will do? We will do this. We have a loop from V number of vertices. We will see why this is up to V times. Do for each vertex, this is another loop, each edge U comma V belongs to E. We check whether we could relax. So, we take a edge U comma V and we check whether we could relax this V or not. Do if dV is greater than du plus, then we do the relaxation. So, this is basically what is our relaxation. This is the relaxation step, relaxing the relaxation. Okay. So, we have a outer loop. This outer loop is working up to V times, V minus 1 times, order of V times, and in the inner loop this is also working up to the number of E times. Basically, this is, we are checking each of the vertices. So, we have many vertices in the graph. We are checking each of the vertices. This is one vertex, and we are checking whether we could relax that corresponding V or not. And this, so the number of, huge number of relaxation we are doing. So, this is the way. Now, after doing this huge number of relaxation, if we still could relax a edge, that means there is a chance of negative cycle. So, that means definitely there is a negative cycle exist in this graph. So, that check we need to do, because we are doing branch of relaxation, even though afterwards after doing this many relaxation, if we could relax further, then we have a problem in the graph. So, that means we should report it negative cycle. So, that step we need to write. Now, this is the last step. This is to report the negative cycle. For each edge, now we will just check if we can do one more time relaxation, then there is a problem. If dV is greater than du plus delta uv. then there is a problem, because we after doing so many relaxation, if we could do further relax, if we could further relax the vertex, then we report negative cycle. So, that means shortest path will not exist. So, it is either giving us the shortest path deltas of s comma v, or it will report a negative cycle. So, let us so what is the time complexity for this, because these are two loops, one is this v loops and one is e loops. So, time is basically v comma e. Okay. Now, let us just execute this. Let us take a graph. So, let us take a graph A, B, C, D, and then say E. Okay, and let us have this edges. So, and then so B to this, and we have D to C, and here, here, and here, and here, and let us just have the weight. Here we are allowing the negative weight also. So, there is no problem to give the negative weight. So, 1, 2, this is 2, this is minus 3, these are the edge weight, this is 5. Okay. So, now what we need to do? We need to number the edges, because in the inner loop we are running this for each edge every time. So, if we could number the edges, it is easy, our job will be easier, we can follow that same numbering. It is not necessarily, you can have in the second time for I is equal to 1, we have to check this for all the edges. So, if you have a numbering, it is easy, but in the I is equal to 2, you can have different numbering also, but to make it simple, we are just numbering the edges. Suppose this is number 1 edge, this is a number 2 edge, this is number 3 edge, then say this is number 4 edge, this is a number 5 edge, then this is a number 6 edge, this is a number 7 edge, and then this is a number 8 edge. Okay. So, now we write A, B. So, these are all in A, B, C, D, E. So, these are the vertices we have, and we have this initialization, all vertices are infinity other than the source vertex. This is the source vertices, which is initialized by degree 0, all other vertices are infinity. Now, we will check. So, these are 0, all are infinity. Now, we check with this. So, for I is equal to 1, so this is for I is equal to 1 step. We check the vertices, we check the we check the edges, we take each of edge. So, we check edge number 1 and we see whether we could relax this vertex. So, this is u, this is v, no, because this is infinity plus 2 infinity. So, no gain. So, we check edge number 2, nothing, edge number 3, nothing, edge number 4. Yeah, for edge number 4, this is u, this is v. So, then this has a chance of relaxing this edge. So, this will become now minus 1. Okay. So, this is become minus 1, and then edge number 5. Edge number 5 is also, this will become plus 4. This is C, so this will become plus 4. Then edge number 6, edge number 6 will also, we can try to see that. So, this is minus 1, then plus 3. So, this is 2. So, 4 will now change to 2. So, this is now 2. So, this is 2. Okay, then 7, number 7 edge. So, this is u, this is v. So, no change. So, number 8, both are infinity, no change. So, this is for I is equal to 1. Again, we have to take for I is equal to 2. Now, for I is equal to 2, again we start from edge number 1, but we could use the different numbering also in this case, but for simplicity we will use the same numbering. Edge number 1, so edge number 1, this is u, this is v. So, the degree of this was infinity. Now, we have a path, we can go from S to this node with a cost minus 1, then we can take this direct path with 2. So, this is plus 1. So, this will be plus 1. So, E is now plus 1, and then we have edge number 2. Edge number 2 is also changed. So, this is minus 2, this is plus 2. So, this will be again plus 1. So, this is D, D is also plus 1. Now, so edge number 3, edge number 3 is this one, this is u, this is v. So, this is 1 and this is 1. So, we have a path from S to this node with a cost 1, then we can take the direct path. So, this is 1, 1 plus 1, 2, which is not better than minus 1. So, we will not change that. Then edge number 4 we check, edge number 4 also remain unchanged. For edge number 5, we have this is 0. So, this is 0 plus 4, which is not better than 2. So, we are not doing anything here. So, edge number 6, edge number 6 also, this is minus 1, this is also remain same. Edge number 7, edge number 7 is 1 plus 5. So, 6, which is not better than 2. So, we will not do the relaxation. So, edge number 8 also, edge number 8 means this is u, this is v. So, we have a path from S to this node with a cost 1, and then we can take this path minus 2. So, this is minus 3. So, this is basically minus 2. So, this will be minus 2 for due to the edge number 8. So, this is now minus 2. Okay. So, now this is for I is equal to 2. Now, for I is equal to 3, we check I is equal to 3, again we follow the same path. So, 1 there is no change, 2 there is no change, 3 there is no change. So, that is it. So, this is the, these are the basically deltas. So, it is converging. So, even for I is equal, what is the number of vertices? Number of vertices is 1, 2, 3, 4, 5. So, we are doing this up to 4 times. Even for I is equal to 2 times, it is converging. But if there is a negative cycle, even after running this outer loop 4 times, even though we have we could able to do the relaxation for some vertex. So, that is the indication that there is a negative cycle, but in this case there is no negative cycle. So, it is converging. So, and these are the deltas. So, this is the execution of this Bellman Ford algorithm, and this is the runtime. Okay. Now, the question is why we are going for this many times this outer loop, why it is order of v times. So, that we have to check, that is the correctness of this code. So, let us just write the correctness of this Bellman Ford algorithm and try to see why it is v times. Okay, so, correctness is coming from this theorem. Theorem is telling we have a graph, and suppose there is no negative cycle. This graph contain no negative cycle. Then after running the Bellman Ford, we should have this degree of each vertices is basically delta of S comma v for all v belongs to this. Okay, so, to prove this, what we are doing, we take a vertex v and we take a path from S to v. Suppose this is v1, v2 like this. dot 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 V k like this, a simple path from S to V. And since there is no negative cycle, so that means we can just, this is a shortest path. So, can we write this delta of S comma V I is basically delta of S comma V I minus 1 plus W of V I minus 1 V I. This is coming from optimal substructure. If we have a shortest path from S to V, then subpath will give us the shortest path from S to that node, and this is also shortest path from S to this. Okay, so, this will give us the proof idea. So, we are trying to see why we are the outer loop is why V times. Okay, so, now we can claim that delta of S, which is basically we can denote as V 0. Delta of S is basically 0, which is basically delta of S comma V 0, because since there is no negative cycle. So, to be so if we are in S, is better way to remain at S, because there is no other way we can minimize that cost, because there is no negative cycle. Okay. So, now, so after the first pass, after I is equal to 1, this means after first path, the outer loop I is equal to 1. So, this is an edge in the graph. So, this edge numbering we have. So, at some point of time, if this edge number is 1, then we are lucky. So, it will be immediately it will change, but it need not be this edge number is 1. So, after first path, after I is equal to 1, so this h will change and this degree will be basically change it to delta of S comma V 1, because it is basically delta of S comma V 0 plus W of V 0 V 1, and by this result it is basically delta of S comma V 1, because we do not know the numbering, but we know that if we taking the all the edges, then this h number will come in I is equal to 1 in the first sort. So, this will give us this after first sort, this degree of this will be delta of S comma V 1. Then after second sort I is equal to 2, since this is done, then this will be again I is equal to 2 sort, this will be delta of S comma V 2 degree, because it will change, because this edge is also an edge in the graph. So, this edge number will come, may not be in the next immediately, but it will come. So, once it will come, it will update this degree by the delta. So, this is the correctness. So, now how many is in a simple path, what is the maximum number of vertices? Maximum number of vertices is V. So, that is why we have V minus 1 vertex in the middle maximum. So, that is why our outer loop is from 1 to V minus 1. So, this is the correctness of this Bellman Ford algorithm. So, now we will have an application of this Bellman Ford in a linear programming problem. So, how we can solve a LPP or linear programming problem using a Bellman Ford. So, in a linear programming problem, basically what we have a matrix A and we have some variable x which is less than equal to b, and basically we have a matrix say m by n, or to be simplicity n by n, and we have a vector x1 x2 xn which is less than equal to b1 b2 bn. So, this is the constant, and then we have to maximize or minimize some objective function c prime x. So, c1 c2 cn. So, this is a general LPP problem, linear programming problem. So, here we will take some particular case of linear programming problem, where this matrix is having only two elements +1 and -1, remaining are 0. So, that means only two element plus 1 and one is minus 1. That means, our this inequalities is of the form x I minus x j less than equal to some w I j. So, for example, suppose we have three variable x 1 x 2 less than equal to say 2, x 2 minus x 3 less than equal to minus 3, x 1 minus x 3 less than equal to 4. So, this type of form we are restricting ourselves by this. This is also called linear constant. So, we will see how we can solve this linear constant with the help of Bellman Ford algorithm. So, this is also called difference constants. Okay. So, how we can, suppose we have some inequalities like this, how we can view this as a graph. So, basically suppose we have this x 1 minus x j less than w I j. So, we will create two nodes like this V I, and then we will have a vertex from this node to this node with the weightage this. So, for this graph, so we have three vertex x 1, x 2, x 3. Now, this will give us a connection over here with 2 and 2 to 3. So, this will give us a connection over here minus 3 and 1 to 3. So, this is minus 4. So, this is if we have a linear constant, how we can view the graph. Okay. So, now the question is, suppose we convert. So, we have a linear system of constant equations, we convert into a graph. Now, the question is, if this graph is having a negative cycle, so that also can be detected by Bellman Ford. We can run the Bellman Ford algorithm on this graph, and we can, if it is detecting a negative cycle, then there is no solution exist for this system of constant. So, how to prove that? So, this theorem is telling if the constant graph, contain a negative cycle, then the system of difference that means system of that is linear is unsatisfactory, it is not feasible. That means there is no solution for this, is unfeasible, no, there is no solution. So, how to prove that? Suppose there is a negative cycle in the corresponding graph. So, that means suppose this is the negative cycle V 1, V 2, V 3 dot dot dot, again it will come to V 1. So, weight of this path is say negative. So, this is starting from V 1, it is going to V 1 with a negative weight. So, this will correspond, suppose these are the weight. So, this will corresponding to the equation like x 2 minus x 1 is less than equal to w 1 2, x 3 minus x 2 is less than equal to w 2 3 dot dot dot, x k minus 1 is less than equal to w of k minus 1 comma k, then finally x 1 minus x k is less than equal to w k comma 1. Now, if we add this term will be gone, all this term will be gone. Here we have 0, and this is here we basically weight of this path, weight of the cycle, which is basically negative. So, that is the contradiction which is less than 0. So, that means this system should not have a solution, because it is contradicting this. So, this is the proof, if a graph is having a negative cycle, then it is not having a solution. But the other way around, suppose we are having no negative cycle, then can you get the solution for this linear constant? Yes. So, that will show. So, suppose there is no negative cycle in the corresponding graph, no negative cycle, then we should get the solution. So, how to get the solution? So, let us just introduce a new vertex S from any other vertex V 1, V 2, V 1, V 2, V 3 like this. So, we just put the edge with all other vertices from this vertex and the edge weight we put 0. So, we are introducing a new vertex. So, we have a corresponding graph, we are introducing a new vertex. Now, this if the original graph is having no negative cycle, this graph is also having no negative cycle, because we have only introduced a 0 weight. So, if it is having no negative cycle, so that means if we run the Bellman Ford, it will give us a delta. So, delta S comma V for all V belongs to this. Okay. So, now we take two vertices V 1 and V 2. So, this is basically delta of S comma V 1, and this is basically, suppose there is a direct edge, this edge we are denoting by W I j, and this is basically delta of S comma V j. Now, by triangular inequality we can say like this, delta of S comma V j, sorry, this is say I and this is j, we take a just a inequality, then we take the corresponding graph part, then delta of S comma V j is less than equal to delta of S comma this path, delta of S comma V I plus W I j. Okay. So, this is basically giving us delta of S comma V j minus delta of S comma V I is less than equal to W I j. So, this is the solution. So, these deltas are basically x I, x j. So, this is giving us these deltas basically giving us the solution for the this difference constant. So, if we can solve it, if we run the Bellman Ford on this, we got the deltas, and that will give us the solution for the linear constant. Thank you.